So in this short one, we're going to introduce the next piece of new content, which involves eigenvalues and eigenvectors, as well as similarity, as well as the idea of bases. So before we do that, I'm just going to go back. Hopefully you've watched the short video on similarity, but I want to remind you what that is here. So when we say that two matrices are similar, what we mean is that there exists this third matrix P, and it has this conjugation property. When you do this, you multiply on the left by P and on the right by P inverse, or equivalently on the left by P inverse and the right by P. In that case, you'd have to change P to a different matrix, namely P would be P inverse. But the point is, when you have this relationship, you say that A is similar to B, and it's similar through the matrix P, which has to be invertible, otherwise this doesn't make sense. And again, just to say from the last video, the reason why this is a sort of symmetric in the sense that if A is similar to B, then B is similar to A, is that if you right multiply by P and left multiply by P inverse, what you'll see is that B equals P inverse A, P, and so this is the property. So in general, what we've talked about in the last video is that two matrices are similar if and only if they have the same eigenvalues. And the reason why that happens is sort of going to be explained in this, well, yes, if they completely have the same eigenvalues with the same multiplicities. But we're going to sort of explore that in this video. In particular, we're going to talk about how to construct one of these matrices P, and we're going to talk about special matrices that are similar to a given matrix. So I just wanted to remind you what similarity was. And remember, if you go back, this statement is correct, but the matrix that makes them similar is not this one. This was a mistake, and I got caught off guard at the end of that video. But in the posting, when I posted the video, I showed you what the actual similarity transformation is. So this is wrong. These two matrices are similar, but they're similar via a different matrix P. Okay, so we're going to talk about diagonal matrices and what's called diagonalization. So one of the facts that we did not prove, and I have to give you some intuition for this when I come back next week, but when you have a family of eigenvectors and those eigenvectors correspond to distinct eigenvalues, what you know is that all of those eigenvectors are linearly independent. And so this is sort of what I wrote here. If an n by n matrix has n distinct eigenvalues, then for each eigenvalue there will be an eigenvector, and you know that those n eigenvectors will necessarily be linearly independent. And the reason why this is interesting is because in this situation, and in general, when you have n different linearly independent eigenvectors, if you're working in n by n framework, then that means that you have a basis of eigenvectors. And this is really useful because this is sort of where we started the whole discussion about eigenvectors. We know that for each eigenvector, the action of the matrix is just scalar multiplication. So these eigenvectors are special in that they sort of see through A, they see the underlying structure of A, so that when A acts on them, all that happens is some multiplication by a constant. And so if you can rewrite your vectors in terms of these special vectors, then you've somehow simplified the action of A. And this has a lot of relevancy in a variety of problems in application. You don't want to work with an arbitrary basis. You want to work with a specific basis that makes your life easier, and that would be this basis of eigenvectors. Now, unfortunately, it doesn't always happen. It's not always the case that you can construct such a basis, and there are several ways this could fail. For instance, you could not have n distinct eigenvalues. That's one way. Or in particular, you could have some situations where you have an eigenvalue, but you don't particularly have enough linearly independent eigenvectors to construct a basis. So a sufficient condition to guarantee that this basis will exist is when you have n distinct eigenvalues, because for an n by n matrix with n distinct eigenvalues, you know that you have one eigenvector for each eigenvalue, and you know from this fact, which I haven't proven yet, that the eigenvectors corresponding to these distinct eigenvalues are necessarily linearly independent. That gives you n linearly independent objects, and therefore you have a basis for Rn. Okay, so let's just look at an example with 3. So we're going to suppose we have a 3 by 3 matrix A, and we're going to suppose we have 3 distinct eigenvalues. So that just means that they're not equal to each other. No, 2 of them are equal to each other. And in that case, they can be complex, they can be real. Just remember, if you have real entries in your matrix and one of your eigenvalues is complex, then one of the other eigenvalues has to be its complex conjugate. That's a fact we talked about before. So for this argument, It's completely irrelevant whether they're real or complex. So each eigenvalue comes with an eigenvector. And remember, really, each of these is just a particular selection of an eigenvector, because each eigenvalue actually corresponds to a linear subspace, which would be the subspace little s times v1, little s times v2, little s times v3. And each one of those three forms a subspace of R3, where s is a free variable. But for now, all we need is one eigenvector that goes with each eigenvalue. And these are the defining properties. So a v1 equals lambda 1 v1. That's the property for this one, so on and so forth. So what we're going to do is we're going to construct a similar matrix, which has a very nice structure, to A, and we're going to do it by constructing the similarity transform P. So remember, what we're looking for is we're trying to write that A is in fact equal to this multiplication of these three matrices, and this will say that A is similar to a matrix D. And what's going to make D special is D is diagonal. So the matrix D is the matrix that has each of these eigenvalues listed on its diagonal and is 0 everywhere else. And the matrix which gives the similarity transform is P, and that P is the matrix of eigenvectors corresponding to these eigenvalues. So this identity holds, and we didn't actually prove this, but I'll do that next week. It's a clever little argument. So the idea is that we can verify this formula, but this will work. So if you want to diagonalize a matrix, right? If you want to diagonalize a matrix, you can do this when that matrix has n distinct eigenvalues. So what you do is you form the diagonal matrix that has the distinct eigenvalues on the diagonal, and then you compute. If you've already computed the eigenvalues, you've computed the eigenvectors as well. Then you form the matrix which has the eigenvectors in the columns, and note that this v1 has to go with this lambda 1, this v2 has to go with this lambda 2, this v3 has to go with this lambda 3. And when you've constructed this matrix P has an inverse. It's necessarily invertible, and I will leave that to you to think of why. Right? Remember that these eigenvectors in this case are necessarily linearly independent. Right? So you have three linearly independent vectors because they form a basis, and therefore this matrix is necessarily invertible by the invertible matrix theorem. So P inverse exists. In general, you don't need to compute it, but the point is if you have P and you have D, then you've constructed this similarity relationship. So the matrix A is similar to this diagonal matrix, which just has the underlying eigenvalues on its diagonal, through the similarity transform, which is a matrix corresponding to the eigenvectors as its columns. Okay, now I want to relax our hypothesis a little bit. So we said before that a sufficient condition for this was that an n by n matrix has n distinct eigenvalues, meaning none of the eigenvalues can be equal. But that's a little too stringent. We can actually get away with a little bit less. So if you have an n by n matrix, it might have an eigenvalue that's sort of repeated. So in the characteristic polynomial, you might have something like lambda minus 1 to the fifth, let's say. And so obviously that would correspond to one eigenvalue that's been repeated 5 times. But as long as you get the same number of linearly independent eigenvectors as the number of repeats in the characteristic polynomial, you will be fine. And so the way we say that is if you have an n by n matrix and you do all the work of finding the eigenvalues and eigenvectors, as long as you can construct n linearly independent eigenvectors, this should say eigenvectors, not eigenvalues, as long as you can construct n linearly independent eigenvectors, then you can still diagonalize. The only trade-off is if you have any repeated eigenvalues. So if you have an eigenvalue that has multiple linearly independent eigenvectors, the vectors will show up here as columns, but then if lambda 2 and lambda 3 happened to be equal, then you would just put the same eigenvalue in both places here, and you would put the two different linearly independent eigenvectors here. So I wrote here that you should compare 1 and 2, because again, this is a condition that will guarantee diagonalizability, namely that this procedure will work. And here, this is a weakened situation where it will work, but this condition is a little bit harder to check. At the end of the day, the point is that when you go to diagonalize a matrix, you need to compute all of its eigeninformation. So you go through the process of finding the eigenvalues and eigenvectors. If at the end of the day, for an n by n matrix, you have found n linearly independent eigenvectors, then the matrix is diagonalizable and the conditions will work. If you want to work in a simpler situation, if you can verify when you're doing the eigenvector process that you have n distinct eigenvalues, then you are guaranteed the process will work. So it's worth it to understand both of these. One is a weakened condition from the other, but I wanted to mention them. Okay, so I wrote here that we'll discuss why this matters soon. What I mean is we'll discuss why diagonalizability is actually a useful thing, and that will be in a video forthcoming probably on Thursday. So for now, just trust me that doing this is useful, and it's useful. I'll just give you a teaser because working with diagonal matrices is very easy. Diagonal matrices have a lot of nice properties. So if you have A and you want to work with A in some capacity, it may be quite difficult to do so. However, if A is similar to D and D is diagonal, then you can get away with a lot of things that make life easier. And we'll give you some examples. Just for terminology's sake, diagonalizable is just the phrase we use to describe what I said before. Namely, an n by n matrix is diagonalizable when there is a basis of eigenvectors. And in particular, that just means that you have n linearly independent vectors. So I just wrote it here, and I just told you what the scoop is. So let's do a couple of examples. So first example, I wrote ha ha ha. And so the reason why is because if you understand what diagonalizability means, you'd be looking for a diagonal matrix that this matrix is similar to. Well, if you just stare at this, this is a diagonal matrix, and therefore it is similar to itself. The similarity transform would be the identity matrix, the 3 by 3 identity. If you put the 3 by 3 identity here and the 3 by 3 identity inverse here, 3 by 3 identity inverse is just the identity, you just see that 1, 2, 3 diagonal is similar to 1, 2, 3. So you don't need to diagonalize a diagonal matrix, it's already diagonal. Cool, that's good. Great. By the way, for something like this, if you have a 0 on the diagonal, that doesn't change anything. So this would still be a diagonal matrix if there were a 0 there. And just remember that if 0 is an eigenvalue, that tells you something about lack of invertibility of a matrix. So if 0 is an eigenvalue and has a non-trivial eigenvector, it means that the matrix isn't invertible. But from the point of view of diagonalizability, 0 is a perfectly legitimate eigenvalue, and it can give rise to a perfectly legitimate non-trivial eigenvector. So again, if you were to put a 0 here, that would tell you that 0 is an eigenvalue, and you would be able to find a non-trivial eigenvector for that corresponding eigenvalue. So what we're going to do is we're going to do a 2 by 2 here from scratch, and this will take a little bit of doing, and I'm going to skip some steps just because it's a very long procedure. By the way, from the point of view of a quiz or an exam, if you have to diagonalize a matrix, that problem is going to be worth a lot of points. So A, it's worth practicing, and B, it's using several different skills, as you're about to see. So I made up this 2 by 2 matrix, and I want to try to diagonalize it. Now, first and foremost, I don't know whether or not it's diagonalizable. I'll only find that out once I've computed the eigeninformation. So we just jump to the eigeninformation, form the characteristic polynomial, which is the determinant of a minus lambda I. Remember, at this stage, lambda is unknown. And so I write this out, subtract lambda off the diagonal, compute the 2 by 2 determinant, 1 minus lambda minus 1 minus lambda minus 2 times minus 1, which is minus 2. And when you factor this, distribute, you get lambda squared minus 3. This can be solved, so you set it equal to 0. That gives you the characteristic equation, and the roots are plus minus root 3. So these are real distinct roots. I now go down to two different null space problems, two different calculations. So this calculation corresponds to lambda equals plus square root 3. And this calculation corresponds to lambda equals minus square root 3. So I want to solve this system to find a non-trivial vector. In particular, I really want to find a one-dimensional subspace of vectors that has this problem. So I solve the augmented system corresponding here, solve the augmented system corresponding here, and it looks like this. And so from here, I just read off that the first column in both cases is a pivot, the second column in both cases is a free variable. So you write out this, and this gives you your one-dimensional subspace. This is called an eigenspace for the eigenvalue lambda equals root 3. And this is the eigenspace for the eigenvalue lambda equals minus root 3. So we have two distinct eigenvalues. Each eigenvalue corresponds to an eigenvector. Those two eigenvectors are necessarily linearly independent. So we have a basis of eigenvectors. And so this satisfies both of our criteria for diagonalizability, the stronger and the weaker. Namely, since we had two distinct eigenvalues, we automatically know that this is diagonalizable because it's a 2 by 2 matrix. But we actually found the eigenvectors, and we know that these two different eigenvectors are necessarily linearly independent because they correspond to two different eigenvalues. So we now know we can diagonalize. And so following the procedure before, what we do is we construct a matrix D, which is diagonal. We put the eigenvalues on the diagonal, root 3 minus root 3. Then we line up the eigenvectors. This eigenvector is the one that goes with this eigenvalue. This eigenvector is the one that goes with this eigenvalue. And then what we have is A equals P, D, P inverse. And notice I did not compute P inverse. I could if I wanted to, but this diagonalizability procedure will work independent of that. So by specifying D and P, then I've implicitly specified P inverse because I know that this matrix is a matrix whose columns are linearly independent and is hence invertible. So then this identity holds. So what I actually asked you to do here is to pause the video, compute P inverse however you like. You can use ChatGPT or just do it by hand for practice. And once you have P inverse, what I want you to do is actually multiply these three matrices together. So take P, multiply by D, and then multiply by P inverse, and check that you get the matrix that we started with up here. Cool. Okay, we're going to do one more sort of involved example, and I'm going to skip even more steps because it's 3 by 3. But there are a lot of places here where if you'd like practice, you can pause and verify that what I'm saying is true. Okay, so here's my matrix, which was painstakingly constructed. It's a 3 by 3. And our goal is to check what the eigenspaces are, and if we determine that this is diagonalizable, then we're going to diagonalize it. So subtract lambda off the diagonal because we're finding the eigenvalues, compute the characteristic polynomial, which looks like this, and then factor it. If you know how to factor cubics, it's conditional, it depends on some values. If you don't know how to factor cubics, you can always just ask Wolfram or ChatGPT if you're working on a homework, and if you're in the situation of a quiz or an exam, I will tell you how to factor, or if you're stuck, you can always come up and ask me, and I will help you factor. But if you factor this out, what you see is that you have one real root and then one complex conjugate pair. So I wrote that out in this way. This is the product that gives you the characteristic polynomial. So the characteristic equation, you set this equal to 0, you extract the roots. So that means we're going to have to do 3 different calculations. Lambda a minus lambda IV equals 0 for each of the 3 lambda i's. And so I did those calculations, I did them offline, and I got that this eigenvector corresponds to this eigenvalue, this eigenvector to this one, and this eigenvector to this one. And so once I have my 3 linearly independent eigenvectors, I know they're linearly independent because the eigenvalues are distinct. Then I form my diagonal matrix, and then I form my P matrix, my similarity transformation. And I just make sure that this is the eigenvector for this eigenvalue, this is the eigenvector for this eigenvalue, and this is the eigenvector for this eigenvalue. If you permute them, right, if you change the order, this will still work. And the reason why it will still work is because if you change the order in D and P, you'll also change the order in P inverse, and so you can still get the same answer. So what I'm saying is the order that you list the eigenvalues and eigenvectors does not matter as long as you're consistent. How you list them in D is how you must list them in P. And as before, what I mentioned you can do is you can check to make sure, right? So just do the calculation, compute P inverse, or use a tool to compute P inverse, and then perform the matrix calculation P times D times P inverse, and verify that you get back what you started. And that, my friends, is diagonalizability. So the next video will be posted in a day or two, and we'll explicitly talk about why we would ever want to do this and what advantage we gain when we do it.